Hey, 42 here. In 333 BC, Alexander the Great led his army into the Phrygian capital of GORDIUM in modern-day Turkey, where, as the story goes, he found an ancient wagon. The yoke of the wagon was secured with a nest of knots so intricate it was impossible to see how the rope was tied together. Legend had it the wagon had belonged to Gordius, the father of King Midas, and according to an oracle, whoever was able to undo the massive knots would become the ruler of all Asia. Since conquering the known world was quite high up on Alexander's to-do list, he immediately had a go at unraveling the ropes, but with no success. After muttering a few Macedonian expletives, the young king took a step back and looked at the problem from a different angle. It occurred to him that it didn't matter how the knot was untied, just that it was broken. So, he took out his sword and sliced a knot in half. Just the sort of thing you'd expect from someone whose surname is the Great. Alexander would go on to prove the oracle right by building an empire that stretched across 3 continents and covered around 2 million square miles. Whilst the Gordian knot became a symbol for seemingly unsolvable problems that require a fresh insight to decode. We have more than a few Gordian knots around these days, like how do we stop climate change? What do we do if we run out of water? And how do we integrate the standard model of particle physics with the theory of general relativity? Okay, that last one probably isn't the top of your mind whilst you're munching on your breakfast cereal or swiping right on Tinder, but it keeps physicists awake at night. Because, unless we answer this question, we may never understand the nature of reality. The problem is this: modern physics is based on 2 major systems that don't agree with each other. The theory of general relativity helps us understand the really big stuff like planets, stars, galaxies, and Kanye West's ego, whilst quantum mechanics helps us understand all the really small stuff like molecules, atoms, and the subatomic world. Both these theories are extremely successful, which in scientific terms means they consistently make accurate predictions. Not that they drive Ferraris and have Deepak Chopra on speed dial. Independently, these theories have revealed the nature of space and the basic structure of matter. But when we try to combine them, things get awkward. For the last 50 years, scientists have managed to ignore the cosmic elephant in the room, but certain questions keep coming up which have highlighted the conflict between quantum mechanics and general relativity. At the center of a black hole, for example, extreme gravity means massive amounts of matter are crushed to a minuscule size, and at the moment of the Big Bang, the whole universe erupted from a microscopic particle. In both these examples, the insanely big and the insanely small are present at the same time. So, we need a set of rules that explains what happens in those scenarios. But neither general relativity nor quantum mechanics alone are able to do that. This is the central problem of modern physics, which is why, for more than 100 years, scientists have been searching for an ultimate theory. A master theory, a theory of everything that could explain, well, everything. This would be the sword that slices through the Gordian knot. And there are currently a few different candidates for a theory of everything, but more on that later. First, we need to understand how we got ourselves in this mess in the first place, and to do that, we need to get our heads around force. No, not the type Yoda uses to lift women's skirts. We're talking about the 4 fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. As anyone with half an hour's worth of gum wrapper education could tell you, the force of gravity was discovered by Sir Isaac Newton, a scientific genius who also established the laws of motion and a whole new branch of mathematics you know and love as calculus, or at least a modern version of it. Though Newton only shared the story much later in life, the legend of how he came upon the law of gravity began in 1665, with him sitting in deep thought in his garden. Ordinarily, he would have been attending lectures at the University of Cambridge, but the school was closed and the students were sent home due to a national outbreak of the bubonic plague. Sound familiar? Newton preferred to rely on observation and testing over theory. This was a guy who, when studying optics, stuck a blunt needle in his eye to see what happened, instead of trusting the textbooks of the time. Like I said, a genius. So when he saw an apple fall from a tree in his garden, he forgot theory and came up with a brand new perspective on what had caused the apple to drop. Gravity is such a basic part of our lives that it's hard to imagine a time when our species had no real clue how it worked. But back when Newton first began developing his ideas, some theologians still believed planets moved due to the beating of angels' wings. And scientific theory was still largely based on the work of ancient Greek philosophers from thousands of years before. It wasn't even called science yet. What Newton studied was known as natural philosophy. At the time, Newton's professors were still teaching Aristotle's view of the world, which was that some substances, like apples, had a quality called gravity, which made them fall, whilst others, like smoke, had a quality called levity, which made them rise. Newton realized gravity is a force that pulls things down to Earth, but his law of universal gravitation went further to say that gravity acts on all objects, including planets. Newton was the first person to understand why planets stayed in orbit and how the force that kept the Earth circling the Sun was the same one that made apples fall from trees. In modern scientific language, Newton unified celestial and terrestrial gravity. Instead of two separate explanations for two effects, both could now be explained by one complete theory. A theory of everything would have the same goal, but on steroids. Unification was also behind the discovery of the second major force, electromagnetism. By the late 19th century, electricity and magnetism had been known for millennia. Magnets occur naturally in the form of magnetite and lodestone, whilst electricity is all around us. Just think of lightning or electric eels. By the late 1800s, a few studies had been published showing a connection between electricity and magnetism, but they were always considered separate phenomena. It wasn't until James Clerk Maxwell published his list of differential equations, imaginatively called Maxwell's equations, that we understood electricity and magnetism to be different expressions of one electromagnetic force. The final two forces we would need to include in a theory of everything are the weak and strong nuclear forces, which were only discovered fairly recently. The strong force was identified in 1973, and though it was predicted in the 60s, the weak force was only confirmed in 1983. But before we dive into those forces, a quick word on subatomic particles. The ancient Greeks believed the world was composed of fundamental building blocks of reality, called atoms, a name which came from the Greek term atomos, which means indivisible. These were thought to be unbreakable pieces of matter, so small they couldn't be seen. Like microscopic Lego that connected in different ways to create the objects we see around us. Like so many ancient Greek predictions, this turned out to be amazingly close to the truth. Researchers in the 19th century proved that common substances like oxygen and carbon were made of smaller units which, as a nod to the guys in togas, they called atoms. By the early 20th century though, it was clear atoms were made up of even smaller components called protons, neutrons and electrons, and in 1913, the world was introduced to the solar system model of the atom that we know so well today. But as technology has evolved and our ability to analyze the subatomic world has improved, even smaller components of reality have been discovered. In the 1930s, physicists discovered the muon, similar to an electron but about 200 times heavier. In the 50s, conclusive evidence was found for the existence of the neutrino, an invisible particle that moves through matter like it doesn't matter. I did a whole video on those mysterious little buggers recently. Then, in 1968, researchers at the Stanford Linear Accelerator Center found that protons and neutrons aren't even fundamental. Turns out they're made up of even smaller particles called quarks. So far as we can tell, quarks truly are fundamental and can't be further divided. And they may not even have size at all, as they're too small for us to measure, even with our highest resolving equipment. But then again, we used to think that about atoms too, so you never know. It may be that as technology keeps improving, we'll be able to keep zooming further and further into subatomic particles, and who knows what we may find. Perhaps at the heart of all reality, there's a tiny old lady making matter out of pancake batter. In a matter of decades, physicists have identified hundreds of different subatomic particles, with names like lepton, tau, and other words you might hear at a Star Wars convention. Physicists needed some way to make sense of it all, and so emerged the Standard Model of particle physics. The Standard Model is considered by many to be the most successful theory ever devised, and it provides a solid framework for understanding and predicting the behavior of particles in the subatomic world. Naturally, without some kind of force, these particles will be moving around chaotically, so physical forms, including you and I, would shift and change constantly. I find it hard enough to keep my shit together as it is. Fortunately for us all, there are at least 3 forces maintaining order in the quantum universe. We've already met the electromagnetic force that, amongst other things, keeps electrons obediently orbiting the nuclei of atoms. The weak force is responsible for particle decay, which is when one subatomic particle, like a proton or an electron, decides it would like to change into a bunch of other subatomic particles for no apparent reason. Without the weak force, we wouldn't have the nuclear fusion reactions that power the sun and produce the energy needed for life on Earth. So it's fairly important. The strong force binds quarks in clusters that make up subatomic particles like protons and neutrons, and also holds together the atomic nucleus itself. If someone at a subatomic cocktail party were to ask the strong force what it does for a living, it would say something like, "I'm responsible for the underlying stability of all matter." Then it would down a bottle of tequila and ride away on a unicorn made of fire. Unlike gravity and the electromagnetic force, which can operate across great distances, the strong force and the weak force only work over incredibly short distances. We're talking just a couple of femtometers at the very most. How big is a femtometer? About the size of a proton, so yeah, pretty damn small. Perhaps, unsurprisingly, the strong force is the strongest of forces, followed by the electromagnetic force, which is 100 times weaker, and then the weak force, which is 100,000 times weaker. The strong force is 6,000 trillion times stronger than gravity, which in the world of forces is a total wimp. Gravity doesn't even show up at a quantum level, so it's not included in the Standard Model of particle physics. And so we arrive back at our original problem, the conflict between classical physics, which is based on gravity, and quantum physics, which is based on the other 3 forces. Things first went awry in the late 1800s when it was realized Newton's laws of motion and James Clerk Maxwell's laws of electromagnetism contradicted each other, particularly when it came to light. According to Newton, you could catch up to a beam of light if you ran fast enough. According to Maxwell, you couldn't. This disagreement was eventually resolved by Albert Einstein, whose theory of special relativity proved that space and time are relative, not fixed as people had always believed. Quite a few physicists needed a stiff drink after that one. Unfortunately, Einstein's genius was about to bite back because the development of the special theory of relativity set up a new inconsistency, this time with Newton's well-tested universal theory of gravitation. Einstein's work concluded that nothing could travel faster than the speed of light, but Newton's calculations suggested gravity operated across vast distances of space instantly. Clever clogs that he was, Uncle Albert fixed that issue too, using a new and improved notion of gravity he detailed in his 1915 creation, the general theory of relativity. This hypothesis suggested space and time are warped and curved by matter and energy, and these changes to the space-time landscape are responsible for what we experience as gravity, which isn't actually a force at all. But once again, in solving one problem, Einstein had only highlighted another. In the early 20th century, physicists, including Einstein himself, began developing the field of quantum mechanics. and it soon became clear that gravity and the theory of general relativity didn't apply at the quantum level. At the same time, electromagnetism, which was the only other force known at the time, couldn't explain the many mysteries of the cosmos on its own. Einstein became obsessed with the problem and spent the next 30 years searching for what he called a unified field theory, a framework that could explain all of physics from the macro to the micro. But as you've probably worked out by now, Einstein never succeeded, and nor has anyone else. Today, there are a few candidates for a theory of everything that might unify the three forces of quantum physics with the gravitational force of classical physics, but for now, they're just that, theories. There's been little or no evidence of these working in experiments, so we definitely can't declare any of them to be true. Perhaps the most promising pretender to the crown is string theory. This mathematical model proposes all the different subatomic particles known to science are not particles at all, but rather hypothetical strings that vibrate in different ways. According to this theory, the vibration of a string, amongst other things, determines whether it will show up as a proton or a quark, or something else entirely. For this model to work, the universe needs to have many more dimensions than the 3, or possibly 4 if you want to get all fancy and include time, that we're familiar with. Most likely 10, whilst the strings themselves need to be one-dimensional, so they only have length, no width or height. Don't try to imagine it. Seriously, your brain will explode. Just like Rocky movies, there seemed to be a never-ending stream of new string theories. So, in the late 20th century, scientists gathered the 5 string theories that existed at the time under a more general framework called M-theory, which, presumably just to one-up the other string theories, requires 11 dimensions. Weirdly, nobody really knows what the M in M-theory stands for. The best guess is membrane, but apparently it might also be master, matrix, mother, magic, or monster. Clearly, nobody has the faintest idea, so I'm going to assume it stands for mango. At the moment, the only real rival to mango theory is something called loop quantum gravity. The basic idea is that the universe is not continuous like we think it is, but rather a series of absurdly small chunks linked together. Where these links get twisted or braided, particles form. Like string theory, there is no experimental proof this theory might actually work, and probably more concerning, nobody's found a way to incorporate gravity. So as a theory of everything, it might be a bit useless. Other theories include quantum Einstein gravity, quantum graphity, internal relativity, and E8, an 8-dimensional mathematical pattern with 248 points that can be used to map the fundamental forces and particles of known physics. To understand what those guys have been eating, watch my recent video about magic mushrooms. None of these approaches has had enough research and support to be tested as a true theory of everything, so it seems we're still pretty far off. But what does that matter? Would anything in your life change if you suddenly understood the ultimate theory? Probably not. Still, it would be kind of nice to be able to say we've defeated the final boss and completed physics, just to show off. Thanks for watching. You can now buy my new book, Stick a Flag on It, on Amazon, or get the audiobook on Audible. You'll find a link to both in the description below. Thank you.